All right, well, welcome back to the day 2 of the Gen AI for Science workshop. We had great discussion yesterday, lots of interesting talks and discussion, and it's again good for us to remember that asking the right questions is the most important thing. We don't have the answers, we don't have to have the answers, but we are at that stage in this revolution that we know there's a lot of excitement, there's a lot of possibilities, but the road ahead is very long. To get to the kind of problem that we want to solve, we need to address a whole bunch of issues, and I think that's what you have to keep in mind. So as long as we keep asking the right questions, we have a hope of getting there. So we have a series of talks and panels today. There's in the morning session, we have 2 talks and 2 panels. In the afternoon, we have 1 talk and 3 panels and a conclusion. I'm very excited. I'm learning a lot from all the questions being asked. And sometimes we have answers, but that's okay. You know, the questions are the most important one. So with that, I'm going to hand it over to Professor Anand Grama, who is going to now introduce the 2 speakers and get started on the panel. Thank you.
Thank you, Dr. Kumar. It is my distinct pleasure to have 2 of my dear friends, one from my childhood and one from more recent, wonderfully talented people. Our first talk is by Professor Ganesh Subbarayan. Ganesh is in the mechanical engineering department at Purdue, incredibly talented, smart person, leads the Purdue Smart Institute for Digital Twins for It's a very large project funded by the federal government. Ganesh has done incredible work on both on data-driven digital twins and mechanistic digital twins. I've had the pleasure of seeing Ganesh talk in many, at least a couple of instances, and I said, we must have Ganesh over here. So I'm sure we'll enjoy Ganesh speak. Ganesh, thank you so much.
Thank you so much, Anand. That was a very, very generous introduction on the part of Anand. I don't know if I deserved it, but thank you so much for the honor of being here. I made a title because I wanted to focus on the importance of data generation automatically for what we want to do for AI. But I'm going to meander a little bit, if you will, to get to that point. So I'll talk a little bit about, so I'll start with some historical background and sort of like tell a story, if I may. So I'll start with my overall theme is modeling for design optimization. And more recently, ML modeling for design optimization. So I'll start with this example. This is from a long time ago. So we were trying to model how bones might respond to prostheses that are, a patient might have a new prosthesis, and you don't want the surgery to fail. You want to understand how bones would respond to the presence of the prosthesis. And the hypothesis is that bones adapt to loads that are applied on them, especially load-bearing bones like our femurs. So, and there's a mathematical way to describe the structure of the bones, and that in turn can help us identify how the bones might adapt when prosthesis is inserted. And it turned out there is a way to formulate this problem as a multi-criteria optimization problem, came up with a variational formulation that you're seeing there as a weighted trade-off between metabolic cost as measured by mass and stored energy, which provides a risk of failure. And that's all, very nicely, those kinds of formulations are all there for many, many bone behavior, animal behaviors, structure, and so on in that beautiful book that I've shown at the bottom there by McNeil Alexander. And what I found out was if this problem turns out to be a topological optimization problem, what you're trying to do is at every point in that structure, you're trying to change the density to find what is the optimal density driven by that criteria. And that is a large number of variables, optimization variables, and for each change in variables, you're going to have to do the analysis. And it turned out for one iteration of optimization, it took about 16 hours on the computer that we had at that time. So it was not going to be very efficient. However, if you could somehow spend the effort to figure out the analytical sensitivities and implement them, you could solve it in 3.5 minutes. So what that taught me was that all the problems, typical engineering problems, analysis problems, are more expensive on the analysis side than on the search side, and then on the optimization side. You might have thousands of variables. Finding the next search in a direct search method is far quicker than the step that requires analysis. The analysis, therefore, we need to do everything we can to speed up the analysis. So one thought, and this has been consistent thought in all of, at least in mechanical design optimization, is maybe replace the analysis with a surrogate model. And the surrogate model might be a machine learning model. And this is not a new idea. This idea originated in mid-90s, I'm going to say, mid-90s. So then we started to explore machine learning models in late 90s and took a set of example problems, some of them very simple, like the ones that you see on two-variable problems, algebraic problems, and some that look a little bit more complex, structural problems. And we went through and evaluated, using machine learning models, how the neural networks perform on these class of problems. And as with any algorithm, what you're trying to figure out is what is the trade-off between accuracy and efficiency. And what you find is what we found was that machine learning models were, at that time, with the resources that we invested in building those models, were not very good. We spent significant amount of time for training, and the red box here is the time it took to train and then to do the inference on the trained model, compared to what it would take for a classical optimization, which builds a series of local approximations and progresses downhill on the local approximations. So it takes far more effort to train, and even then you don't get very good accuracy. Your errors in function value percentage can be pretty large, is what you're finding here. 80% error in variable values, 20% error in function value, etc. So not doing very well. So the message to me from this learning experience was that you need to invest a lot of time in training the model. And if training is an important part of the overall solution process, you're not going to be efficient. So if training can be done offline somehow, then you can be more efficient. So then later, we worked on another example, and this example is on device color mapping. We were mapping color between, say, the monitor to the printer. This is a project that IBM was very interested in. IBM was, at that point in time, marketing room-size printers. IBM got out of the business. So I'm an ex-IBMer for Lior. So IBM got out of that business. But they were trying to figure out how to map color from the monitor to the printer, because their customers wanted to make sure that if they were buying a room-size printer, those printers produce colors as accurately as they could. So this is the gamut mapping problem. So color can be represented in a three-dimensional space in a device-independent manner, but the printers and the monitors don't represent colors the same way. Printers represent them subtractively, monitors represent them additively. So you have now in the color space, you need to go from this triangular shape, which is what the monitor produces, to range of colors that monitor produces, to the hexagonal shape, which is the range of colors that a printer produces. And the one that you see there, IBM Teak, is the one that IBM was manufacturing at that time. So we needed to figure out a way to map from the triangle to the hexagon. So we came up with, again, what we did was to print thousands and thousands of swatches of color and measured them painstakingly. This is what a grad students do, right? Unfortunately, this poor grad student had to measure 7,000 patches of color. And then we were able to build a machine learning model, a neural network model, that we were then able to use to correct on the fly the colors that the printer would produce for a given image on the screen. So we were able to patent this, and this is around 2000 or so. We were able to do this, and this told me that, again, this I learned from my previous experience, that here training time is not critical. I can do it offline. Now I can use the trained model to do the inference very quickly, and that was more important here. I was able to do that. So more recently, this is some work that I have ongoing with a colleague of mine, Dan Jiao. More recently, we're looking at modeling for advanced packaging design exploration. This is a topic that's very close to heart to Sachin here. So so one of the drivers for this is that the energy cost growth of AI computing is exponential. And it's expected by 2030 that, depending on who you believe, the number could be anywhere between 10 to 30% of total energy produced is going to be consumed by AI. So depending on who you believe. But the energy resources that are available to us are limited. So we need to figure out a way to reduce the energy. And this is where advanced packaging has been proposed as a way to, the ideal would be if you do everything in a single chip, but if you, at least for performance-wise and energy-wise, but the fact that cost drives us to not make single chips larger than about 858 millimeters squared forces us to break the chip into smaller chiplets. And those chiplets you want to integrate as closely as possible to consume less of energy. Here's an instance of one of those examples of AI-oriented advanced package, and it has many elements in them. It has high bandwidth memory, a processor that needs to communicate with the high bandwidth memory, because now we are trying to push through trillions of parameters of our AI models between the processor and the memory. So this processor memory communication is the biggest source of energy cost, and that needs to be somehow minimized, which means you need to bring these things as close as possible to each other, ideally, if possible, to stack them on top of each other in three-dimensional stacking. So in this design process, you need to explore alternative configurations of these chiplet arrangements, and that in turn has, design would require criteria like, does the resulting package have the right electrical characteristics, right thermal characteristics, and right mechanical characteristics, because this package could warp, etc., could have high temperature. So what we did was to, again, explore for various configurations. We wanted to come up with a machine learning model that can handle it's trained with all the possible configurations, not just that, but all the possible flux boundary conditions that you might have, convective boundary conditions that you might have. So we didn't address generality of Dirichlet boundary conditions, but the Neumann boundary conditions were general. Any arbitrary Neumann boundary condition could be. So we trained the model. It required 3,200 training data points and 800 testing data points. And with that model, it was able to produce accuracy on an average of 0.0053 kelvins and test times, which are much, much smaller than 1 second. Now, to build this sort of a model, this is a key point that I want to make. To build this sort of a model, one needs to automate the analysis procedure, because the biggest, by a Sandia study from 2005, the biggest bottleneck to finite element analysis is really the mesh generation. So it's about 50 to 75% of the time in the 2005 study was mesh generation. It's the human in the loop that you want to eliminate, which means you need to be able to automate your analysis, take all the possible different boundary conditions, power maps, configurations, and be able to automatically analyze them. That, in turn, what it required us to do is to come up with a data structure to describe the geometry and automatically mesh it, assign power maps automatically, assign boundary conditions automatically, solve, and then interpolate, and then develop the network. So that's the part that I want to emphasize. So finally, I will leave with some couple of thoughts. And this is all inspired by Anuja's presentation yesterday. So and Anuj was generous enough to share his presentation last night. So I had some opportunity. So one thing that that I've learned over my career, I started off as a computational modeling person, but I've more and more, when I work with industry, I find that I don't get enough insight with computational models, and the insights are far better with analytical models. So I find that as we go from, say, computational models, numerical models to analytical models, my insight is better. And the insight is even less compared to computational models with data-driven models. So is there any way for us to provide that insight from a model that's constructed purely from, abstracted purely from data? Here's an example. So this is a project that I would give to my students who believe that anything they see on a screen produced by finite element code is accurate. So I'll give them an analytical problem and ask them to estimate the error for various meshes. So they'll do convergence study and find that their finite element model is often pretty far off. So is there something like this that we could come up with for machine learning models? Are there standardized tests? Finite elements have patch tests. Those qualify the elements. So do we have something equivalent to a patch test? Do we have validation procedures for machine learning models? Is there something we can come up with? So here's one thought. And the other is recently we've also been exploring physics-informed neural networks. These are linear PDEs. And what we find is what you're seeing in the screen is this data point is the finite element model analysis. The x-axis is mean percent error. The y-axis is computational time. And that's where the finite element sits. And all of these are different architectures of physics-informed neural networks. We find that no matter what the architecture is, even 100 by 100, it doesn't quite produce the speed and efficiency, the speed and accuracy of the finite element solution. So I think, in my opinion, physics-informed neural networks are not efficient or accurate yet, but they have the potential possibly. Here's one more thought. We know that overfitting is very common in machine learning models. Here's a simple analytical function. I generated data from that analytical function by adding noise. And I fit different curves to this data set. One is the blue dashed lines are polynomials. They're going to be highly oscillatory. This is something that's well known in CAD, mechanical CAD, but nevertheless it illustrates a point. The blue is highly oscillatory, and that is my polynomial. And the red is the cubic Hermitian, and you can see the green line is the machine learning model. The reason why it's jiggling is because if I move 1 point, the whole machine learning model curve changes quite a bit. So it doesn't have what is called the local control. If I change at 1 point, all I want to have is a local region to change. These are some well understood properties in computational mechanics. There is this property called partition of unity. That property ensures, and compact support, that property ensures that if I move a node, the influence is local. And there is also this partition of unity property assures me that if I have convergence in a local region, I assure convergence in a global sense. Is there any assurance of convergence, or is there any tunable level of smoothness that ML can produce? These are all questions that came up to my mind based on my background. And the last question is, can we provide more insight? More insight. So for instance, if I have physical systems, I can construct governing equations numerically as k times u equals f. And then I can differentiate it, and I can semi-analytically calculate sensitivities. And that tells me something about the system. Now, is there a way for me to do the same thing with an ML model? Can I somehow estimate sensitivities? How do I systematically infer more about the behavior of ML models rather than treat it like a black box? So these are all some questions that came up to my mind. And the last, I will just spend a couple of slides on the new opportunity that we have. And Anant was very gracious in talking about the digital twins and the Smart USA Institute. It's a new opportunity for ML as well. So this is the Federal Institute that was stood up last November. It's a $285 million award by the NIST to SRC, Semiconductor Research Corporation. And those are the founding members there. When it comes to digital twins, it's not just the computational models, it's not just the machine learning models, but they need to have a bidirectional feedback with the equipment, with experimental equipment. So the models are corrected by data from experiments in a continuous loop in real time. So this is a new opportunity. The model needs to be fit for the purpose. You cannot have one model, one size model for all. Then it also, it's more than just simulation because there needs to be this continuous feedback. It's process being guided by models and models being refined with process data, manufacturing process data. And of course, you need to also verify, validate, and UQ of these digital twins. So with that, I'll stop and thank you for your time.
A nice presentation. I got a good overview of the computational issues. The question I have is in the first thing you had done, I guess the stresses optimization. So in terms of the input data, because for neural networks, you need a lot of training data. So this training data, you kind of simulated them or you kind of got it from somewhere?
No, you basically, you have to train your machine learning model, neural network model. So for each function evaluation, you go do a finite element analysis, or in this case, matrix analysis.
So I wanted to understand better the matrix, the graph you put up showing that physics-informed neural networks are both higher error and more computation than standard PDE solutions. My understanding is that that is true if, in general, okay? However, the reason there is excitement about PINNs and generally the use of machine learning to solve PDEs is because many problems have a structure where a large part of the PDE solution is dumb and boring.
I'm sorry.
Is dumb. It's repetitive. It's,
okay.
You have to go through the loops to do it, but it's not interesting. And those parts, you can basically jump over if you're doing it through neural networks. And so there might be some things that we can say about the structure of the problem that would change the conclusion that you have on that slide.
The way I'm looking at it, I'm a computational mechanician. Bhaskar here is a computational mechanician. I would love to hear his thoughts as well. The way I look at it is neural network here is just another basis function for solving a boundary value problem. So in that sense, you should then ask the question, what is the efficiency of this basis function versus a standard Lagrangian function, for instance? So in that sense, I feel there needs to be more work. We need to still prove its convergence. Yes, neural networks are universal approximators, but are they any more efficient than, for instance, the Lagrangian functions we know very well? We know their convergence very well. So that's where I'm coming from. I said this is preliminary. This is, I know experiences will be different.
So if I can add to that, right? So from a, again, computational mechanics standpoint, from our experience, from a forward model perspective, if you have to solve a single equation one time, in this case AX equals B, I think we have 60 years of linear algebra, numerical linear algebra codes. I don't think any machine learning model can compete yet. But so in terms of a single forward simulation, I think conventional scientific computing beats pins, other things right now, right? So purely because we are solving AX equals B problem versus we are solving half AX square minus BX optimization. But when it comes to like what your point about when you're looking at, if you can frame this as a problem of a family of PDE solves, then I can amortize the cost of training the machine learning model on multiple instances, and then the cost of during inference instances from that family, then we are much better with solving using machine learning. That's where I really like your problem of framing this as an optimization problem where you have the same class, a family of PDEs, and then you can amortize the cost. So.
Yeah, fair enough. Thank you. Agreed.
Thank you, Ganesh. I really appreciate the one thing that you mentioned about verification, validation, and EQ. There is a ASME committee on that called ASME. VV10 committee, which is on computational mechanics, 20 is for nuclear and structural, I think. So I started almost 8-9 years ago VVUQ for advanced manufacturing, especially using machine learning and AI and all that. So your point is very well taken. In fact, the committee has actually published 2-3 standards now. The foundational problem is, what do you mean by validation if it is completely data-driven? Okay, so you don't know the physics, you're trying to understand the physics and things. So that's one of the questions that people are trying to answer in terms of how do you go from simple regression model to causal relation, and we are not there yet. So I think you're raising the important point there. I strongly would like you to come to that VV50 committee and probably give a seminar there. I think we have many, many companies in that committee. So I'd really appreciate if you can come to that.
Thank you very much, Sudarshan. That was very kind of you. I just want to say that I just want to add a point. Sandia, for instance, has set of benchmark problems for fracture problems, for instance. Maybe this is a time to generate those sorts of benchmark problems.
I'm also a mechanics guy. I'm glad to see that you're attempting that. And sometimes we say naive question. Your finite elements, so each element you have a basis function, then you're constructing your Ku equal to F, right? So if you do the finite element, you got the K, and with the neural net or machine learning, can you come back to a basis function for the whole thing? I know reduced order model, different concepts are going on, projection methods and all.
Yeah.
Did you venture into any of those kind of things?
Indirectly. So this problem, you can turn this into a multi-level hierarchical problem. Anant and I have discussed it recently. So it's a multi-level hierarchical problem. Then the only way you can do that, in my preliminary opinion at least, is that you need to have sensitivities. So you can poke the model, try to get sensitivities, and construct some information about the model. If it's a linear system, then it becomes relatively straightforward. The problem is most of our problems are not linear. So then how do we construct information about the system? So we need sensitivities to start with. Even for UQ, you need sensitivities to start with.
You remember we used to have a lot of work on floating point arithmetic and round-off error, floating error, truncation error, etc. So I have not seen anybody talking about that in neural networks or machine learning as if they think that they have infinite precision. So how do you become computational mechanics and all that? One of the biggest problems they consider is if it is a truncation error. That is the whole idea of random number generator. You force it, and then a deterministic algorithm is trying to generate a random number. So you may get that in neural networks too. So I have not seen much of that work. Have you seen some of that?
No, I'm not very familiar with that aspect of that.
I can answer that a little bit, Sudarshan. So there is not so much from a stability perspective. There's a lot of work on speeding up neural networks in the energy perspective, where there are these empirical results that you find that the early layers of the neural networks you can quantize a lot. So you can get away with 8-bit arithmetic in the front layers. The back layers you tend to need more and more precision. And you can more or less maintain the backward accuracy of what you're trying to do an inference from. There are other ways of characterizing sensitivity as well. So for example, there is understanding of how the rank structure of the weights changes through the networks. So in fact, there's some very interesting results where you can argue that the total information content through the network stays the same. In other words, more information flows through the middle layers, the rank actually goes down, but then the rank goes back up at the back end of the neural network. And there again, the motivation isn't so much sensitivity analysis, it's how little computation I can get away with. So for example, if you have a dense layer from layer 1 to layer 2, you don't have to train all n square weights. You can get away training k times n weight, treating it as a low rank matrix as opposed to an n by n matrix.
Yeah, I mean, those are many techniques like that. But going back to what Bhaskar said, at the end of the day, you have to solve Ax equal to b. Whether you're going to do sparse matrix or whether you're going to do canonical transformation, making into diagonal matrix, requires floating point arithmetic.
So let me use my moderator's prerogative here. to add my perspective to Bhaskar's perspective and Jack's perspective as well. You're absolutely right. If you know, it's kind of like saying that if I have multiple right-hand sides, let me use the LU factorization and I can use the LU over and over again. So it's kind of like saying, let me train a neural network. If I have multiple right-hand sides, I can do this over and over. The only difference between what we do there and what we do here is there are no bounds on generalizability. So if you have a domain that's dynamic, you have discontinuities, you have inhomogeneities, you are pretty much at the mercy of the neural network. You have no idea what you're going to get the second and the third time you're going to do inference. That is the only part that scares me there. But that said, let me argue against myself, because I like arguing. In these cases, I think forward error is not as important. So did you get your simulation error? Did you get the simulation quantities right is not as important as saying whether you got the objective function, the design parameters right at the end of your objective loop. So you could be you make all kinds of mistakes in your simulation, but if you give me the right objective parameters, do we really care if you made all of those mistakes? That I have never understood. So smarter people than me probably need to.
Yeah, that's a question that needs to be resolved in my mind. That's very critical in my mind for a machine learning model to provide me insights. If I didn't pick the right variables, how do I know what is the right? So that insight is lost. I can do that with analytical models. That was my point.
We'll take one more and then maybe we can. Yeah, last question.
Thank you. So in this training of using surrogate model for optimization, one of the perennial problem we have is that the surrogate model deviates from the raw model, right? So sometimes people have this continual training, online training to keep it authentic. I wonder if you guys do that sort of thing.
So this work was done 25 years ago. We didn't do any continuous update of the surrogate model. So we basically built a surrogate model to try to get as low an error as possible. And given I don't remember all the details of when we stopped the training process. And then we basically used it compared it against a classical optimization approach where we are constructing local models. That's all we do.
Yeah, they veer off to different paths because when you search
it wasn't a dynamic problem, this was a static problem. So in that sense, you know, it's it wasn't as much to see if the time evolution of the response changed, veered off. It was just to see how close we got to the final solution.
Thanks, Ganesh. Thanks. Let's thank the speaker again.